Okay, I guess it's time to get started. It's good that we have a lot of people. Given that this is the 5th lecture, plus we have issues with coronavirus, as you know. If you're not feeling well, you're welcome to go out. In fact, that's your responsibility to go out. Because you can have all of this online, as you know, right? Okay, how was last week? Did you have fun? Okay, so we started with the labs last week and also a combinational logic. Today I'm going to continue, so we're going to have a lot of fun this week also. We're going to finish combinational logic today, and we're going to talk about memory, meaning sequential logic, tomorrow. So by the end of tomorrow, you will know how to build a very simple microprocessor, really. Of course, we're not going to build up the microprocessor immediately. But before I start, you have an assignment, watching my inaugural lecture and doing there's an optional assignment which gives you 1% credit. I put a deadline for this, March 25th, because if I don't put a deadline, then people won't finish it. It's always good to have deadlines, so you have 20 days to finish it. And this is really easy. You just review the lecture and you get 1% extra credit for the course, which is a freebie. And hopefully the lecture is fun also. Okay, the second assignment, this is important. As I said, readings are optional, but they will help you understand the material much better. And I assign a lot of readings. And at the beginning of the course, we will have many more readings, because the beginning of the course is really where you're building your background on what comes afterwards. In fact, toward the end of the course, we will not have any readings. There is no book that really covers what I'm going to cover, starting from the middle of the course, actually. But the beginning of the course, I would recommend doing the readings. Especially these days, you're staying at home because of the coronavirus. You have a lot of time, right? So it's great to do the readings. So this is the combinational logic chapters. I'm going to cover what you need to know for the exam, but if you don't understand something, I would recommend going to the readings for sure. Combinational logic is for last week plus this week, and this week plus next week, we're going to cover these readings. So basically, by the end of next week, we're going to finish roughly, because we're not going to cover everything that's in these chapters, clearly. Roughly, Pat and Patel chapters 1 to 3, and Harris and Harris chapters 1 to 4. Okay, so if you do the readings, and again, as I said, you don't need to do both of them. You can choose one book or the other, or you can choose none of them. If you're understanding everything perfectly, no problem. But I would recommend doing these. And I also refer to some of these readings when I talk about some parts that I explain. Okay, so this is where we were. We were talking about combinational logic circuits and design. And I'm going to jog your memory a little bit. Basically, what we covered last time was we started from the transistor as a building block of computers, and then we built logic gates on top of them, and we built combinational circuits on top of them. And we were talking about the correspondence of Boolean algebra with combinational circuits. Boolean algebra is essentially a functional specification of a combinational circuit. These are completely different things, clearly, but Boolean algebra maps nicely, because combinational circuits work in binary form. I assume many of you learned about Boolean algebra, so I'll ask the question again. How many of you know about Boolean algebra? Okay, that's good, most of people. How many people don't know about Boolean algebra? Okay, that's good, no hand. How many people know about De Morgan's law? Okay, that's a lot. So we're going to cover things. How many people don't know about De Morgan's law, or don't remember? Okay, don't be shy. Okay, I don't see any hands. So I'm going to go relatively fast on the Boolean algebra part. But this is really important to understand combinational circuits, because we're going to do some Boolean algebra in homework as well as the exam. You can be sure that there will be a question related to what I'm going to talk about today on the exam, because this is really so important for designing and minimizing circuits. So basically, we're going to talk about how to use Boolean algebra to represent combinational circuits. And we're also going to talk about how to minimize logic circuits by doing algebraic operations, as well as some other ways. Basically, people wanted to automate the minimization of logic circuits, because you can clearly express the same operation in many different ways using Boolean algebra, but people wanted to find the minimal ways of expressing them, and people wanted to find a way of getting to that minimal way in a methodical fashion. So in the end, you basically want to build the engineering where you start from point X to go to the minimal. How do you minimize a circuit? So we're going to talk about that. I'm not going to give you all the steps. If you really want to know about all the steps, you really need to take a logic synthesis course. Again, that's offered at the ETH, for example. Basically, logic synthesis means you start up with a circuit, and how do you actually synthesize that circuit, hopefully automatically, to a minimal form, or to a form that actually satisfies your needs. So people actually try to automate this, and a lot of it is really automated today using computer-aided design tools. So we're going to see some things that computer-aided design tools do automatically, but we're going to do that by ourselves. Okay, does that sound like fun? Okay, cool. Remember, we're at the bottom of the stack still. We learned about the transistors. We forgot about the transistors. Don't forget about how they work. But we're at the higher level of abstraction right now. We're not going to the transistor level as much, except for the recall slides that I have over here that are going to jog your memory, hopefully. So basically, in the last week, we learned about how a metal oxide semiconductor transistor works. And we talked about how do we build logic out of those transistors. So basically, we start from the devices, that's the transistor. And then we basically started constructing basic logic structures out of those individual transistors. And those logical units are named logic gates. And these logic gates implement simple Boolean functions. And this is an example, basically. This is in complementary metal oxide semiconductor technology, which you should know by now, at least the high level, not the microelectronic design details of it. But basically, this is a NOT gate. It's an inverter. It consists of two transistors. And it's represented by this truth table. And it's represented by this logic gate. And essentially, its Boolean equation is y equals a bar, right? That's the Boolean representation. And this is a NAND gate, as you can see. It's this is the transistor level structure of it in CMOS. And this is a truth table, and it's an AND. So you could keep going. And this is an AND. And an AND is constructed using a NOT and an inverter. Remember, I mean, there's a good reason for it, and we briefly discussed it. CMOS is very good at inverting because these transistors that are at the top are good at pulling up, and these transistors that are at the bottom are good at pulling down. In the end, it's an inverting logic, meaning that inversion operations are much more reliable in CMOS. That's why a NAND gate is much more reliable than an AND gate. In fact, if you want to build an AND gate with CMOS directly, it's not easy. Okay, so basically this is all material from last class. Basically, this is the general CMOS gate structure. You have a general form, you have a pull-up network with PMOS and positive MOS, and a pull-down network with negative MOS. And essentially, you can construct any inverting logic gate. Inverter is one example where you have one transistor over here, one PMOS transistor over here, one pull-down transistor over here, right? And the networks may consist of transistors in series or in parallel. And when transistors are in parallel, the network is on if one of the transistors is on. Clearly, that's parallel, right? If any of the parallel structures is on, you basically conduct. When transistors are in series, the network is on, meaning that the network conducts only if all transistors are on, clearly. And this we discussed last time. Frank discussed that. This is slower, clearly, because things are implemented in series, and you have to go through all of these transistors, and each transistor has a resistance and a capacitance, and as a result, that delay is much longer, whereas parallel is much faster, right? And that's fundamental. That's very fundamental. Basically, this is the fundamental principle. Parallel is faster than serial. At the transistor level, at the core level, at any level. If you have a parallel machine that you can utilize well, that's going to be faster than serial. Okay. Okay, so I'm already spending a lot of time on this, right? People are clear on this? Okay, good. And if you really want to go into more detail, do the readings. Readings go into a little bit more detail. But if you really, really want to learn how these transistors work, you need to take a microelectronic design course. And those design courses are actually very, very interesting. You learn about how the transistor really works. You learn about the switching properties. You talk about different transistors. But for that, you need to take a course, that course from ETH, for sure. So you can go one level below the abstraction level also. And you can potentially invent new transistors also, actually. That's something that's being done today, for example. People find out that the transistor technology with which we build our current computers are not good enough for various reasons. Power consumption is one reason. So people are building transistors that are much more power efficient, that can switch at extremely low voltages. Because if you switch at 5 volts, you're consuming a lot of energy. If you switch at 0.01 volts, that would be nice, you're consuming a lot less energy, right, and power. And that's another recall, basically. So this is very critical today. Speed of the transistor is very important, but power consumption is also very important. And we discussed last time that there are two components to power consumption, dynamic versus static. Dynamic means whenever you're switching the transistor, meaning turning on and off, you're consuming some power, and this power is correlated or represented with this sort of equation, basically. It's proportional to the capacitance of the circuit. If you're looking at just one transistor, it's just that transistor. But if you're looking at a circuit like a big logic gate, you also have the capacitance of that. It's proportional to the voltage at which you're turning on and off. And it's proportional in a quadratic manner, as you can see. Meaning that if you have 5 volts supplied, you're consuming a lot more power consumption. If you have 0.01 volts, you're consuming a lot less. That's why people are building transistors that are switching at very low voltages. Now, the downside is switching at very low voltages is not easy. Because when you switch at very low voltages, you may not be able to switch very well. So reliability reduces. Again, this is a very fundamental principle also. If you want to reduce the power consumption, you may become less reliable. So there's this fundamental trade-off between power saving and reliability. You can save a lot of power, but you may start getting bit flips, meaning your transistors are not only smaller, but you're switching them with very, very small voltages. So you may not be able to switch reliably, so you may get a wrong bit, right? Wrong value. This transistor may not conduct, for example, even though you wished it to conduct. So today's technology, actually, if you look at the technology that goes into the cutting-edge processors over here, they're at very small, very low voltages. And they run into the risk of getting these, I'll call them bit flips, but getting these faults that may cause the transistor not to work very well, especially under all circumstances. So you remember the Rove-Hammer effect. This is another effect that could potentially affect the reliability of systems going forward. And they may be happening. So if you use this system, for example, in space, it may not work very well because the conditions over there are very different. If you use it at 140 degrees Celsius, again, it may not work very well. First of all, it's not specified for use at 140 degrees Celsius. But if you use it, it may not work very well because some of those transistors may not be switching very well. That's true for lower temperatures also. Okay, and the last one is basically charging frequency of the capacitor, how frequently you're charging. That's really the clock frequency, as we will see later on. So you can see that there's this complex dependence of power on capacitance, voltage, and frequency. And it turns out, actually, if you want to operate at high frequency, if you want to switch really fast, you also want high voltage. So you basically get this double equation. So if you really want to increase the frequency, meaning increase the speed of your circuit, speed of your transistor, you also want to increase the voltage. So frequency is correlated with voltage also. So you essentially have a cubic relationship between power consumption and voltage in today's processors, which is a bit unfortunate. The fortunate part is, of course, if you reduce voltage, you're reducing your power consumption in a cubic manner. So voltage is a big hammer in reducing dynamic power consumption. Make sense? Okay. So power consumption is important because let's say you have, I don't know, 20 billion transistors, right? In a GPU, you can clearly have 20 billion transistors today. Let's say all of them are switching at the same time. Basically, all of them are consuming power at the same time. And if you're, in the end, if all of them are switching at the same time, you need to be able to supply the power that's needed for all of them to be switching. And that means that your power supply needs to be strong enough. That means that your thermal design point needs to be high, meaning you don't want you to burn your hand, right, while using this, because it's drawing a lot of power. So that's why power consumption is very important. Right? There's also another aspect to power consumption, which is static power consumption. And that's basically, even if you're not doing anything, which is what's happening right now over here, there's some leakage that's happening in the transistor because it's connected to the power supply. So basically, some of these transistors are leaking over here because they're connected and they're not perfect. And as you reduce the size of the transistor, that leakage also increases. And that leakage current causes some static power consumption. It's essentially voltage times the leakage current. So this is becoming worse in future systems because transistors are becoming smaller and smaller, and that leakage current is increasing. And that threshold voltage is also, of course, again, if you want to save power, you reduce this threshold voltage. It's called threshold voltage at which the transistor switches. So that voltage is very good for, reducing voltage is very good for reducing power consumption. Okay. So basically, even if you're not using your computer, it's leaking. This is very similar to DRAM refresh, right? DRAM refresh is also leaking. DRAM capacitor is leaking when you're not using your memory. this transistor that you put for logic is also leaking when you're not using it. Now, the difference is DRAM is actually much worse in terms of leakage. It turns out the capacitors, we do not know how to build capacitors that are less leaky. We know how to build transistors that are less leaky, more or less, but capacitors are very hard today, especially at the small sizes that we want them to build, want them to be built at. So this is becoming worse, and this is also becoming potentially worse as we keep adding more transistors into the system. So power consumption is really, really important. That's why I'm harping on this slide, even though we didn't really discuss in detail. So there's also energy. I know Frank discussed it, but energy is essentially power times time. You should remember this from your physics classes. This is important for your battery life, for example. And I think Frank gave the example of, you may make energy 0, but you may not get any work done, right? Basically, your time becomes infinite, your power becomes 0. That's one way of making your energy 0, and power 0, but that's not a very good thing. So in the end, today's systems are complex systems where you try to maximize performance while minimizing both power consumption and energy consumption at the same time. And these are 3 different things in the end. They're related to each other, clearly. Clearly, time is related to performance, right? It takes some time to execute your program, and that's your performance. And you need to keep your computer powered up during that time, and that leads to the energy. Make sense? Okay, so even this slide gives you an idea of the trade-offs that we need to make in designing current systems. And different systems make the trade-offs in a different way. This makes a trade-off in some way because energy is extremely important here. But power is also very important here, because I don't want to burn my hand over here, right? Energy is also important here, but maybe less important because the battery is much larger, clearly. But power is also still important. Maybe, again, less important, I don't know. Maybe performance is more important here. Although, you could argue, right? It depends on the users as well, right? Okay, so if you want to know more about this, see this little chapter, which doesn't go into a lot of detail. Okay. Okay, so let's go back into the logic gates. So these are some logic gates. These are the truth tables, and I'm going to ignore the transistor level from now on. So we talked about the buffer. We're going to see the buffer. This is to amplify the signal, for example. I think Frank briefly mentioned that, but sometimes you may actually lose the integrity of the signal, meaning the voltage on a wire, and you may want to amplify it. So for example, if you're transmitting from here to here, your wire is very long, and you can think of this as a chip, right? And while you're going from here to here, you may initially have 3 volts, but that voltage drops over time because you're basically carrying electrons, right? And your signal integrity may not be good, so at some point where you really need the voltage to be high, it may be low. So how do you actually rectify this? You basically amplify the voltage. To amplify the voltage, you build a buffer, and there are multiple ways of building the buffer, which we're not going to go into, but one way of building the buffer is having 2 inverters. Before the signal drops, you have 2 inverters, and you basically amplify the signal, right? Of course, that's an expensive way of building the buffer, but that's one way of building the buffer. So the purpose of the buffer is really to amplify the signal. So you can see that logically, it doesn't do anything. Logically, the output gets the value of input, but physically, at the lower level, what it does is it amplifies the signal, amplifies the voltage. So this is one interesting place where if you don't know the lower level of abstraction, you have no idea why this buffer is there. But if you know the lower level of abstraction, then you know that, oh, this is a very long wire, and I may want to insert a buffer over here so that I can amplify the signal. So this is one place where you cannot really perfectly design things at the logic level. You really need to know what's going on at the lower level so that you can make things work. Because you may have a long wire, and if you don't amplify the signal, you may not be able to switch the transistor at the end, right? That's the idea. This is very similar to sound, right? Sound travels across a medium, and if the place where the sound is traveling is so far, you may want to amplify the sound in the middle, right? You basically insert a buffer or sound amplifier, and that amplifies the sound such that the sound can be transmitted to the next room so that people in that room can hear. It's the same thing, basically. Well, same thing at a different technology. Okay, so XOR and XNOR are also interesting. Basically, do people know about XOR? Do I need to talk about it? How many people know about XOR? Okay, it's from your Boolean algebra. Basically, XOR means that the output of the gate is 1 if an odd number of the inputs are 1. So this is, of course, 2 input, but you can generalize it to 3 input, 4 input, 5 input, and XNOR is the inverted version, complement of XOR, essentially. Okay, we're going to see these more and more, and you're going to use them, actually. So Frank started Boolean equations. I'm going to go through this relatively quickly since you know about this, but Boolean equations enable us to functionally specify the output of a circuit in terms of the inputs. Basically, function is a unique mapping from input to outputs, and the same input values produce the same output value every time. So there's no memory. In the combinational logic, we're going to assume no memory because the output is a combinational function of the current inputs. So you don't remember anything from the past. Okay. So full bit, 1-bit adder, we're going to look at this adder later on today. Okay, so these are Boolean not and or. Now you know that very well, but basically, this is how you write things in Boolean. This is A bar, complement of A. A dot B is, or A and B. Essentially, it's A and B. A plus B is A or B. So this also said A times B or A and, I don't want to, no, this is not and. This is A plus B or sum of A and B, right? So basically, you can think of this as a product, and this is a sum, and we're going to use those terms. So basically, it's an algebra, and it's defined by Boole, and if you're really interested, you can read the beautiful book that he wrote in 1847. And he clearly did it without knowing anything about circuits, but this is an algebra that's applicable to binary logic very well. If you have multi-valued logic, that's a different thing, but we have binary in the design of computers today, which is 1 and 0, and this applies really well, and we have some basically, it's an algebra on 1s and 0s that's binary with different operations. And we have some axioms that we know as truth. And we can build laws and theorems on top of that to manipulate Boolean expressions. And using those, we can also do simplification on Boolean expressions. Basically, you may have a very sophisticated Boolean expression that if you map it to and, or, and not gates, it will be a huge circuit. But if you actually use the laws and theorems, you can simplify that Boolean expression, and your logic may be much smaller. And that's the beauty of Boolean algebra, using Boolean algebra to minimize the circuits. Okay, so we're going to see some of that. So Frank talked about a lot of this, so I'm not going to go through this in detail, since you know about this, but I'm going to jog your memory very quickly again. Basically, we have 2 elements, 0 and 1. Result always stays in 0 and 1. You don't get some other value, although we will see later that sometimes you have undefined values like x, and you will have floating values like z. So it's not completely Boolean. Most of it is Boolean, but those values are very special, as we will see. Z means it's floating, meaning that value is not connected to anything. This is really a circuit-level abstraction. So it's not in the Boolean algebra itself. So we will see that. So commutative, basically A plus B is same as B plus A. This is similar to math, basically, right? You have an identity element. A ORed with 0 is A ended with 1 is A. You can distribute multiplication over addition and addition over multiplication. I call this addition and multiplication. They're not real addition and multiplication as we have, but it's Boolean addition and multiplication, clearly. You can think of it as OR and AND. And you have the complement, basically. If you OR something with its complement, you get 1, because it's either A is true or A bar is true. That's logic, right? Either of them has to be true in binary logic. And if you AND something with its complement, you get 0, right? Because it's either A and A bar, you get basically false. Okay, so duality, I think we talked about this also. So I'm going to go through this relatively quickly, but basically, you have duals of all of the axioms. Anything true for an expression is also true for its dual, which is a very nice property. So any derivation you make for one thing is true for its dual. You don't need to make the same derivation over there. So what's a dual? Basically, a dual of a Boolean expression is derived by replacing every AND operation with an OR operation and every OR operation with an AND operation, and replacing every constant 1 with a constant 0 and constant 0 and constant 1. That's it, basically. And don't change anything else. So this is an example. The dual of this equation is this, basically. Basically, what we did is, this is A dot B plus C. We change the dot to plus and plus to dot. And these two are duals. Now, this is showing the distributive property. The multiplication distributes over addition, as you can see. A dot B plus A dot C. So these are clearly correct because of the distributive property. But if you actually take the dual of this, you will get this. Basically, change the dot to plus, plus to dot, and you'll get this. and both of these are duals, and essentially, it's correct, right? So distributive property holds for this as well as its dual. Sounds like fun, right? You've probably seen it, so I'm going to go through it quickly. So clearly, Boolean algebra, there are much more things you can do. I mean, we already talked about this basically. You can do operation with 0 and 1, but you basically have the duals. So you basically change this plus to dot and 0 to 1. You get the same thing, and that's correct, right? X and 1 is X. Because 1, if you AND something with a 1, you should get the value of X. If X is 0, you should get 0. If X is 1, you should get 1, right? Similarly, if you OR something with 1, you should get a 1, because 1 means true, and if you OR 0 with true, you'll get true in the end, fine. And the dual of this is you change this plus to a dot, and you change 1 to 0, and you change this 1 to 0 also, and that's also true. If you AND something with 0, you should get a 0. Right? So that's a beautiful duality property. That's very nice. That's true for idempotence also. Interestingly, this is, yeah, true. Involution is basically if you take the complement, if you take the double complement of something, you basically get the X value, and essentially the dual of this is itself. So that's why it doesn't really have a dual, because there's nothing you change. There's no plus here, there's no 0 or 1 here, right? Or there's no dot here, as you can see. You don't play with the complements in the dual. Okay, it's either X or X bar. That's one. Again, you can take the dual of this. And commutative law is also nice, basically. X plus y is equal to y plus x, and that's true for its dual also. Makes sense, right? It's a beautiful algebra. That's why you should read Boole's book, if you have the time. But this is already very well known, right, as you can see. Okay, there are more interesting things for simplification, potentially, right? Associative laws are very nice. Basically, you can associate things in different ways. I'm not going to talk about that. So here, the order doesn't matter. Sometimes I actually make assumptions on the order, but we will see that later on. Some of you who are careful enough will see that there are some assumptions on the ordering later on. Okay, distributed laws, basically we talked about this. You distribute multiplication over addition and addition over multiplication, and they're duals of each other. These simplification theorems are actually very nice for simplifying circuits. So for example, this one. You have x and y, or x and y bar. That is equal to x. And clearly, I made an assumption in terms of ordering. Ordering means x and y. The AND operation takes precedence over the OR operation. I evaluate this one first, and this one concurrently, and then I evaluate the OR. Right? Normally, I don't like doing that, but for ease of reading, I do it over here. I don't want to put parentheses over everything. So assume that AND takes precedence over OR. So clearly, this is true, right? Because you're ANDing x with y. Basically, how do you actually... well, you can actually show this, right? We're going to show it in the next slide, I think. So this is true for the dual also. Basically, if you have a circuit, if you see a circuit that looks like this, or if someone gave you a Boolean equation that looks like this, it's not a good idea to probably implement it exactly like this. You just implement x, right? You just take x and pass it. Makes sense, right? Okay, this is also very interesting, actually. This happens in a lot of designs, and I see it in a lot of designs sometimes. X plus x and y is equal to x, actually. Why? Because of the distributive law, you will see that if you take out x, this will be x and parentheses 1 plus y, and 1 plus y is 1, and then you get x times 1, which is x, right? And that's true for its dual also. So this actually happens a lot in real circuits. This is also another simplification theorem, basically. You can simplify this equation to x dot y. And you can actually prove all of these clearly. So this is actually very, very much worth remembering because they show up in a lot of real designs. It turns out in real designs, you do some operations, and in the end, you end up with an x value and an x dot y value, and you OR them. And if you do that, you can get rid of that circuitry. It's just the x value that's enough for you. Okay, so basically we can do proving of theorems. So you can prove this one. I actually did this for you earlier in the slide without actually showing this. Basically, you take out x using the distributive law. I actually did this one, I think, for you, but this is actually a very similar way of doing it. And then y plus y bar is 1, clearly, and x and 1 is x. And then that's your identity, x. In the end, you get x. So you can also do this commonly occurring circuit. You basically have the identity x is equal to x times 1, and then you use the distribution law. And then this is clearly 1, and x dot 1 is x, and then in the end, you get x over here. So I can prove a lot of theorems, and this is the basis of simplifying circuits. So this is one way of simplifying circuits. You can actually feed these rules to a program, and somebody specifies a truth table, and the program itself automatically translates that truth table to some sort of equation, and it uses that equation, and it simplifies that equation progressively using these theorems and laws, and then it gives you the minimal circuit. This is called computer-aided design, and that's the basics of minimizing the size of your circuit. And there are tools for this that you can use. It's beautiful. There's a very beautiful engineering theory that's developed for it, starting from 1950s. And you can actually use these tools. Like, actually, some of the old tools are called espresso. People liked espresso when they developed it. So you can actually use that for minimizing circuits. Okay, so let's take a look at De Morgan's law. So you said that you know De Morgan's law, but this is De Morgan's law, and this is the dual of it. Well, they're both De Morgan's laws in the end, since they're the same in the end. But this is basically what it says. It's really a transformation. So I think of it more interestingly like this. Basically, you have f equals a plus b plus c. If you apply De Morgan's law to it, this is what you're really doing. Basically, a plus b plus c bar is equal to a bar dot b bar dot c bar. And if you take the complement of both, they're equal still. So what does this mean logically? This is all logic in the end, right? I like thinking of these laws as logic. So x and 1 is x, because if you AND anything with 1, you should get the value that's provided by x, right? So here, you can think of this logic as, if at least one of A, B, C is true, which is really the English version of what I just said over here. This says A plus B plus C, not. What does that mean? That means at least A, B, if at least one of A, B, or C is true. If this is true, then it's also the case that, well, it's not the case that A, B, C are all false. Right? So this is logic in the end. Basically, this implies this, and this implies this. That's why they're equal to each other. Makes sense, right? That's the basis of these rules. So this may look cryptic to you, but logically they're equivalent in Boolean logic. Okay, so why are these De Morgan's laws useful? They're useful because they enable you to convert different gates to each other. Basically, different types of logic functions. For example, I guess let's pick this one over here. So this is x plus y bar. De Morgan's law says that it's the same as x bar and y bar, right? So this is the circuit. This is essentially a NOR circuit, right? This is an OR, and this is an OR. That's how you specify an OR. And it's equivalent to this thing, which is an AND circuit with inputs complemented. Okay? This is De Morgan's law. So basically, whenever you see this sort of expression, you may convert it to this sort of expression. And this enables you to trade off between two different types of gates. So why is this useful? Well, for example, you may not have every type of gate in your implementation. Usually the way design is done today is you have some certain basic logic gates, and you have this equation, let's say truth table. You specify your logic with a truth table, and some tool maps that truth table using equations to the logic gates. In the end, you want to use the logic gates that are available to you. If you don't have this NOR, you'll use an AND with complemented inputs. Fine. I mean, this is a cooked up example because normally you have NOR and AND. But there is a more realistic reason for doing this. In the past, actually, there were reasons. There were reasons why you didn't have NOR, why you didn't have NAND. But today, you have all these sorts of gates. But some of these gates may be faster than others. For example, in your book, you will see that there is a method for designing a NOR using weak NMOS logic to be much faster than a NAND. So if your NOR logic is much faster than an AND, then you don't want to use this one. You want to use this one. Basically, you want to convert from here to here, or similarly, here to here, right? So that's the idea, basically. You can switch between different mappings of a circuit. So this is, again, very similar. X and Y bar, which is an AND, is equal to X bar or Y bar, right? So you can think of this as an AND, and this is an OR with inputs complemented. This is also called bubble pushing. Actually, you could create a visual expression of this. De Morgan's law is actually, what you do is, you start with this gate. If you want to find the De Morgan of this circuit, what you do is, you basically first push the bubbles, meaning there's a bubble over here. You push the bubble over here, both of them become bubbles, just like this, and you convert the type of gate. or becomes an AND. And that's the Morgan's law for you. So that's a visual representation, clearly. That's true for this one also. Okay, so now I've already given you some idea of how you could use Boolean equations to represent a logic circuit. Now we're going to go a little bit deeper into how we actually do that. Any questions so far? Okay, so basically, we want to have a methodical form to do this. And methodical form starts with a standardized structure. Basically, we have a truth table. That's how you actually specify a Boolean function. How do you express the function in terms of the inputs in a standard manner? And the idea is the sum of products form. And this is going to be very important because this is a very standardized form of representing a truth table in terms of a Boolean equation. Essentially, it's a two-level Boolean equation that contains all input variable combinations that result in a one output. It's basically two-level. The first level is ANDs that give you the all input combinations that result in a one output, and the second level is an OR of those. If any of the input combinations, combination of input variables that results in a one is true, then the output is a one. And then the function is OR of all input variable combinations that result in a one. So this is all in words. Now let's take a look at some pictures, basically. Before I go into the pictures, I'll give you some definitions. Complement, hopefully we know this very well. A variable with a bar. Literal is a variable or its complement. Basically, we refer to literal as a variable or its complement. Implicant is the product of literals. This is very important. We're going to use the implicants in our sum of products, basically. And then minterm is the product that includes all input variables. So this is the standardized way. This may be a simplified version in the end, but the standardized way is you have some inputs to a function, you use all of the inputs in a minterm. And it's the product form, basically. This is, for example, a dot b dot c bar, a dot b, a bar, b bar, c. So if you have three inputs, you need to have 8 minterms, because they can take the two forms of the literal, right? The variable and its complement. We will see that again. Max term is the opposite of this, basically. It's not the dual of this, because we're actually changing the complements, as we will see. It's really the sum or that includes all input variables. We will see this. This is actually going to be interesting with the product of sums form, but let's see the sum of product forms. Basically, this is a standard form of taking a truth table and transferring or translating it into a Boolean equation. It's really, truth table is really the unique signature of a function, Boolean function, but it's an expensive representation. How do you represent a truth table, right? We want to actually represent it as a Boolean logic. And a Boolean function can have many alternative representations, clearly, as we saw, because you can minimize a function, right? And many alternative Boolean expressions may have the same truth table, clearly, right? And also they may have the same different gate realizations, right? So basically these say the same thing. These are the same function, but they may have different gate realizations in the end. That's why we want to start with a canonical form that everything maps to, and then we minimize that canonical form to the minimal form. And we will see that. So what is the canonical form? It's really the standard form for a Boolean expression. It gives you a unique algebraic signature that translates the truth table to that form. So let's form that canonical form for this truth table. So this is a function that I gave you. It's just made up. We're going to convert it to a sum of products form, or express it as sum of products form. This is also known as a disjunctive normal form or minterm expansion, as you will see. Ignore this one, but minterm expansion, it will make sense. Basically, what you do is you find out all of the, so these are inputs, these are outputs. You find out all of the places where the output is 1. And you basically look at what the values the variables should take to make the function 1. So you can see that if A is 0, B is 1, and C is 1, the function is 1. So you take that. That's one minterm, as we will see. If A is 1, B is 0, C is 0, the function is 1. If A is 1, B is 0, C is 1, the function is 1. If A is 1, B is 1, C is 0, the function is 1. If A is 1, B is 1, C is 1, the function is 1. So there are 5 cases. And if any of these is true, then the function is 1. So basically you OR them. And that's your expression of the function, right? Basically, F is true if A bar B C is true, or A B bar C bar is true, or A B bar C is true, or A B C bar is true, or A B C is true. I went through all of this, but it's hopefully obvious, right? Basically, if any of these are true, then F is true. We just converted this truth table to a standard form that includes all of the minterms that lead to the output being 1. And that's how you do it. Basically, let me go over it again. Each row in the truth table has a minterm. There are 8 minterms over here. A minterm is a product and of literals. Literals are A, B, C, or their complement. Each minterm is true for that row, and only that row. And all Boolean equations can be written in this SOP form. Basically, you take the minterms that lead to a true output, and you OR them. And all Boolean equations can be done. If your circuit has, let's say, 10 inputs, you have to do the 10 minterms, and you figure out which ones lead to a 1, and you OR them. And you, of course, write them in this minterm form. That's the idea. So why does it work? Hopefully, it's obvious why it works, but basically, you can simulate. Assume that you formed this function using this minterm. You can verify it, right? Basically, 1, 0, 1 should lead to a 1. 1, 0, 1 activates this term, right? It doesn't activate anything else. This is disjunctive. That's why this is called disjunctive normal. Only one of the minterms can become a 1 if they become a 1, right? Not 2 minterms. Okay, so this activates this term, you get a 1, and that input, and that becomes a 1 in the end, the function. Only the shaded product term will be 1 in the end. Okay, no other product terms will turn on, they will all be 0, so if inputs A, B, C correspond to a product term in the expression, you get this for the output, which is basically only one minterm evaluates to 1, every other minterm evaluates to 0, but in the end you get a 1. And that kind of makes sense because you're really enumerating every single minterm in your function. So if inputs A, B, C do not correspond to any product term in expression, you get 0. Let's test it. Oh, okay. Let's test it. Basically, I have 0, 0, 0. The function should evaluate to 0. And this is my sum of products form. If I apply A equals 0, B equals 0, Z equals 0, none of them will be 1. All of them will evaluate to 0, and in the end, you get a 0, right? So you can basically test it. So this is really our standard notation in the end. So now if you actually agree on the order of variables in the rows of the truth table, you can enumerate each row with the decimal number that corresponds to the minterm. So what does this mean? I mean, this is a lot of wording. Ignore all of that. But basically what I'm saying is, I have a standard form of forming my truth table, A, B, C. There's an order of variables, and I clearly specify 0, 0, 0. Basically, I go from 0 to 8, if you will, in a monotonically increasing form. So this 1, 0, 0 is decimal 4, right? So that's minterm number 4. This 1, 1, 1 is decimal 7. That's minterm number 7. So I can specify a 3-input function based on its sum of products. Basically, minterm 3, 4, 5, 6, 7 are activated in this function, and I can basically say this function is a 3-input function with these minterms activated. I don't need to have a truth table, right? And now I can feed this to a program that really understands what's going on with the minterms, right? Or you can use a summation notation. You can basically specify it like this. This function is specified using these minterms 3 through 7. Okay, so this is the canonical SOP form, basically, sum of products. And essentially, it's a shorthand notation for minterms of 3 variables. Okay, I already said this, I think. So now we can minimize it. Let's take a look at how we minimize it, basically. So someone gives you this function in terms of minterms. You imagine that you're a computer-aided design program. You take this function. You clearly understand what it is. You basically convert it to the minterm. You expand the minterms, basically. This is called minterm expansion. That's what you get. But clear, this is canonical. It includes everything. It's not the minimal form. It's actually, in a sense, well, I don't want to call it the maximal form, because you can always add more variables and make it even more maximal, right? But it's in a sense, the maximal reasonable form. It's a standard form. So now you know the equation, because somebody gave you these minterms, you start minimizing it. One way of minimizing it would be by applying the laws and the theorems we discussed, right? You basically realize that this A bar B is shared, AB bar is shared between this and this, and then you combine them, and then this becomes a 1 clearly, and you also realize that that's true for AB also, and you keep doing this. I'll let you do that, and in the end, this is your minimal form. And a program can do this, a human can do this, as long as we agree on the standard form of representing a truth table, or a circuit you want to build. Okay, and this is a realization. So clearly this realization is much, much more expensive, but any of these realizations are possible, right? Anytime you have this equality, that's the same circuit. So you probably, if you want to minimize area, you want this circuit. If you want to maximize performance, you also probably want this circuit, because then you want to minimize the levels, right? If you want to maximize redundancy, meaning there might be a reason why you want to actually maximize the redundancy, because you may get a fault in one transistor, and that transistor may not work, or one gate may not work. If the other gate works, this form may be better, right? Potentially. Think about it. We're going to get back to that later on. Okay, let me continue and finish this part, and then we're going to take a break. But basically, sum of products leads to two-level logic. So if you actually take this, you can actually represent it directly as logic, right? And this is one example. I don't take the example over here, but this is smaller sum of products. It's clear this is a sum of products form for 3 input variables. But basically, this is the direct realization of that logic. We're going to see the structure later on. This is called a programmable logic array later on. But basically, you can have the inputs like this and the complements. And basically, you connect the min terms that are activated to these AND gates. And you connect the literals. Basically, you connect the literals such that you activate the correct min terms. So clearly, you want A bar, B bar, C here. You connect A bar, B bar, C, and them. You connect A, B bar, C bar, and them. And you connect A, B bar, C over here. And then you OR them, basically. So this is a direct realization of the sum of product form in a circuit. But this is not the minimal realization, as you know. Okay, let me talk about the alternative canonical form. This is product of sums. This is essentially the opposite. Basically, when we formed the sum of products, we looked at the places where the output is 1. Now we're going to look at places where the output is 0. This is really the De Morgan of sum of products of f prime. Now, this may be a mouthful, but basically, we start with these max terms. These are called max terms. Max terms are terms where the function evaluates to 0. And this is basically a product of sums form. Basically, this function evaluates to 0 if any of these max terms evaluates to 0. And you can convince yourself. So basically, for this to evaluate 0, A, B, C, all 3 need to be 0, and that corresponds to this max term. For this to evaluate to 0, A and B needs to be 0, and C needs to be 1, and that corresponds to the other max term. And for this to evaluate to 0, A needs to be 0, C needs to be 0, B needs to be 1, and that corresponds to the next max term, and we're done, because there is no other case where this function evaluates to 0. So this is called product of sums for this reason. Basically, you have the products in each of the max terms, and you sum them up. So, okay, I think I've already given you this, so hopefully it's obvious after this. Basically, you activate this term. For the given input, only the shaded sum term will equal to 0. And if this is your input, 0, 1, 0, this will be 0, and everything will be 0 because it's a product. If you AND anything with 0, you get the 0, right? So I think this is another example. If you give this input 0, 1, 0, this is what you get. So hopefully this is obvious. You can go through this example yourself. Okay, so let me, how do you write this product of sums form? So this is the max term form. You find the truth table rows where f is 0. 0 in the input column leads to true literal, and 1 in the input column leads to complement literal. You OR the literals to get the max term. Basically what we did just now. And you AND together all the max terms. So this is an algorithm, basically. This algorithm can be implemented by a computer, right? Basically, you feed the computer a truth table, it basically gets the max terms, and it basically forms this Boolean equation, and it basically does this minimization of the circuit using all the rules that it has. Or, okay, you don't do any of this. You just remember, product of sums of this function f is the same as the De Morgan of sum of products of f bar. You know De Morgan's law. You know how to do sum of products. I actually like sum of products better, although this is just a preference, because I like thinking of ones, right? If the output is 1, I can form the sum of products nicely. But then if I want to form product of sums, I take the De Morgan of f prime, sum of products of f prime. Okay, so let me finish this part, and then we're going to take a break. Basically, we've already seen this max term. So this is the max term notation. This is very similar to what we did with sum of products, but now we're doing the product of sums. The same function that we saw earlier is product of sums of max terms 0, 1, 2. Okay? It's not the complement of the function. So you should realize that this is very, very important. This is the function itself. If you want to do the complement of the function, it's something else, right? And we will see those rules in a little bit. So you can do the min term to max term conversion. Basically, these are the same function. It makes sense, right? Basically, these are the sum of products form. Yes, sum of products sum. This is a sum. min terms 3, 4, 5, 6, 7. If you want to do the product of sums form, it's basically max terms 0, 1, 2. Remaining max terms. You need to cover both zeros and ones. You do the max term to min term conversion in a similar way, basically. These two are the same function again. Now we can expand f to f prime. It's also relatively easy. Basically, if f is like this, f prime, which is the complement, is really the sum of the complement min terms, which also makes sense, right? A complement of a function has outputs completely inverted, meaning that you just need to take the other min terms that you didn't use for the sum of products. That's true for product of sums as well. And you can also do this. I'm going to skip this. These are relatively simple. Okay, so this is a good place to stop right now. So let's stop. Oh, that's a good time, actually, because this is exactly what I was planning. Let's be back when the bell rings. And then we're going to continue this beautiful part. Okay, so let's continue. So hopefully everyone is clear on Boolean algebra. I know some of you have seen it in some classes, but some of these may not be exactly the same. How many people have seen these sum of products and product of sums form in the past? Okay, you've seen it. All of who has not seen this? Okay, everybody has seen it. So, okay, next year I'm not going to talk about this as much. But hopefully this was a good review of what you've seen. And some of the terminology may be different. So, and you can be sure that there will be questions about this on the exam. No, that's not a hint. That's obvious, hopefully, right? If you look at all of the past exams, there are questions, and these should be questions that are relatively easy, hopefully. Okay, so now what I'm going to do, basically, the reason we cover this is really the building block of computer-aided design tools. You can give a truth table to a computer, and it basically minimizes that circuit. And this is actually very well known. And we will see some fun examples later at the end of this lecture on how to do this pictorially. Clearly, I'm not giving you the full evolution and development of the tool, because that'll take a long time. But you can imagine how a computer actually minimizes a circuit by itself. But before I go into more minimization, let me introduce some of the combinational logic blocks that we're going to use into the future. And this is going to be fun. And hopefully you haven't seen many of these. So basically, combinational logic essentially is often grouped into larger building blocks to build more complex systems. So you have these gates that we discussed, and or not. Clearly those are good. But we usually build larger blocks. And these blocks are there to hide the unnecessary gate-level details, to emphasize the function of the block. So clearly, a computer can take a truth table and map it to and or not, right? But it can also map it to these larger blocks. So that mapping of a function into a block is very, very interesting. And or not is easy, because we can see that Boolean algebra works nicely. You can translate a truth table to a canonical form, and you can minimize a canonical form. In the end, you get and or not. Now, keep in mind, when we discuss these blocks, how can a computer map some higher level structure to these blocks that we're going to see? Okay, so we're going to look at some blocks: decoder, multiplexer, full adder, and programmable logic array. Who has learned about these? Okay, some people. Who has not learned about any of these? Okay, that's good. So programmable logic array, I kind of introduced it, actually. This is a very good match for the sum of products form, actually. It is really implementing the sum of products form in circuit. So you basically program the connections in this programmable logic array, and you basically directly implement the sum of products form in the circuit itself. This is really reconfigurable logic, or configurable logic, let's say. So you can actually map any function to a programmable logic array, as long as the programmable logic array allows you to have that many inputs and the number of outputs that you require. We will see that. So this is the place where you can easily map a sum of products form to a programmable logic array. In your FPGAs, you're going to map some functions to the FPGAs. They will have some PLAs, but they have also a lot of advanced structures. But let's take a look at some functions over here. So let's start with decoder. So now we're going to build things that are bigger than and or not, but we're going to use and or not, or NAND or NOR, whatever. You know how to translate things. So how many people have seen a decoder before? Okay, not many, that's good. Basically, a decoder is really an input pattern detector. Basically, it decodes the pattern in the input. It has n inputs, it has 2 to the n outputs, and it basically asserts the output that corresponds to the input pattern. That's the idea. Meaning exactly one of the outputs is 1 and all the rest are zeros. So you really decode what those n inputs are. Each of them is a binary input, of course, right? So basically, the one output that is logically 1 is the output corresponding to the input pattern that the logic circuit is expected to detect. So let's give you an example of 2 to 4 decoder. This is the truth table, right? So these are the 2 inputs, A1, A0. These are the 4 outputs, 2 to the n, 2 to the 2. And you clearly have 4 cases. And each case corresponds to one output being 1. And these are different outputs, as you can see, right? So this is how we can identify this input. If this output is 1, you know that the input is 0, 0. If this output is 1, you know that the input is 0, 1. If this output is 1, you know that the input is 1, 0. If this output is 1, you know that the input is 1, 1. So that's a pattern detector, basically. This is the simplest pattern detector that you can have. It's also used to determine addresses. For example, you give an address. If the address is 1, 0, only this output is 1. And you use that address to activate the data that you're going to read, right? We're going to see this later on when we build memories. So this is a very basic building block for addressing a circuit or addressing a memory. But ignore that for now. So this is essentially it. So basically, this also to give you some terminology going into the future, the outputs, there are 4 outputs, and you can think of them as, there's a special term for this encoding of the output. It's called one-hot encoding. Only one of the outputs is hot, meaning only one of the outputs is 1 for a given input combination. So it's really one-hot encoding. This is the maximal encoding that you can have for the outputs. Okay? Okay, and this is the high level. We don't know what the implementation underneath is, but this is the high-level module, basically. You have A1, A0, 4 outputs, and this Y3 is activated, or it's a 1 if the inputs are 1, 1. Y2 is activated if the inputs are 1, 0, and so on. That's a 2 to 4 decoder. Similarly, you can have a 3 to 8 decoder, right? A 4 to 16 decoder, a 6 to 64 decoder, right? Basically, the outputs need to be 2 to the n, because exactly one output is 1 for a given input pattern. Okay, so I've already said this, but this is the underlying implementation. Basically here, I don't have I0, A1, but it's essentially the same thing. It's this 2 to the 4 decoder, where the inputs are renamed to AB. But this is how you actually build a decoder, 2 to 4 decoder. You can see that this is A bar, B bar, right? The output is 1 if A and B are both zeros. This gives an output of 1 if A and B consecutively are 0, 1. This gives you a 1 if AB is 1, 0. This gives you a 1 if both A and B are 1. And only one output is 1 because you can see that we've enumerated all of the minterms, actually, in this case, right? So this is a decoder. It looks nice, right? So one example is if A is 1, B is 0, this one is activated, and you get a 1 over here, everything else 0. So this is how you detect a pattern, basically. So what is it useful for? I've already given you examples, but how to interpret a bit pattern, right? Basically, this could be the address of a DRAM row that the processor intends to read from. I want to read from, of course, this is only 2 bits, but I want to read from row 2, 1, 0. And row 2 gets connected to the word line, and you get the data out of there. All memories work this way. You need to have a decoder to address the memory. So if your memory has, let's say, I don't know, 2 to the 64 rows, you need to have 64 bits over here, and you need to have 64 to the 2 to the 64 decoder for that. So you can imagine that's a huge thing, right? But that's how it is. And we will build memories later on. Also, it could be the instruction in the program, and the processor has to decide what action to do. So decoder is useful for decoding what a bit pattern tells you. Bit pattern is a format, right? So for example, we will see later, very soon actually, in a couple of weeks, that we encode instructions using opcodes. Opcode specifies what an instruction does, and opcode is essentially a bit pattern. In some ISAs, the opcode is 6 bits, for example. So you can have 2 to the 6 instructions, and whenever the processor sees an instruction with an opcode of some particular 6-bit pattern, it uses a decoder to figure out what instruction it is. It basically feeds the opcode, 6 bits, to a decoder, to the 6 outputs, and only one of the outputs will be 1, and the processor knows that it's instruction X. And if that output is 1, some logic circuits get activated, and you execute the instruction based on what that instruction is. And you build the circuit that way. That's the idea, basically. That's the beauty of detecting the pattern. You're really decoding the pattern, right? Okay, that's clear? So you will see, you will actually use these to build structures, but decoder is a very useful tool. Okay, let's look at multiplexer. Multiplexer is another thing that's very useful. It's also called a selector. Basically, it selects between n inputs. That's the idea. Basically, it selects one of the n inputs such that it connects that input to the output. So, of course, how do you select it? You need to have a select signal. That's called the select signal, or control input, called select. So if you're selecting between n inputs, you'd better have a select signal that can specify those n inputs. So you need to have a log 2 to the n bit select signal. So you'll see this is an example. So 2 to 1 mux is the simplest mux. The multiplexer is also called the mux, affectionately. It multiplexes essentially. So this is a 2 to 1 mux. So there are 2 data inputs. These are single bit inputs, and there's a select input. Basically, if the select input is 0, you take, the output becomes equal to the data input 0, as you can see. If the select input is 0, you don't care what this is. The output is equal to D0. If the select input is 1, the output is equal to D1. Right? You don't care what this is. So that's the truth table. You select, based on the select signal, the value that you are to pass to the output. And this is the simplest. And this is the high level. I'm not showing you the gate level over here. I will show you the gate level in the next slide. Basically, you have a select input, and you have 2 data inputs. If the select signal is 0, you select data input 0 and pass it to y. If the select signal is 1, you select the data input y and pass it. You select data input 1 and pass it to the output. That's the idea. Now you can imagine, you can clearly do the gate level implementation of this, right? You can actually express a sum of products form or product of sums form. You can minimize the Boolean equation, and you can form my circuit, what needs to go inside here. Clearly, it can be maximal or it can be minimal. So you know how to do this, actually. You know how to convert this into the gate level representation of this module. And this is one gate level representation. And you can see this, right? Basically, you have the select input. If the select input is 1, this becomes a 0, meaning that you're not selecting A, but you're selecting this one. You're selecting B. If the select input is 0, this becomes a 1 and this becomes a 0, because it's an AND gate, meaning that you're selecting A. That's the idea. And you can see that this is sum of products form, right? For 2 to 1 mux. Okay. Okay, basically, you can, this is it. Actually, I should not say that sum of products form. That's a simplified form, right? If you have a sum of product form, you need to have 1, 2, 3, 4 things that are out there. Okay, anyway. You can do that simplification. So this is one example. If select input is 0, as I said over here, this becomes a 1, this becomes a 0, so this evaluates to 0, this evaluates to A, and you get the A at the output because it's an OR gate. Okay, that's a 2 to 1 mux. This is useful when you actually want to pass a value depending on the value of something else. So if the instruction is something, then you use this value. If this instruction is something else, you use this value. So that's useful for data flow in a processor, as we will see later on. Okay, so basically the output C is always connected to either the input A or input B. Output value depends on the value of the select line. I'm going to go a little bit more into the multiplexer. So this is another way of showing the multiplexer, basically. You have a select line, you have A, B, and you decide. So this could be actually multiple bits. It doesn't have to be a single bit. This could be a 32-bit wire. If your select line is 0, you take this 32-bit value and push it out to a 32-bit output. So it could be wider. And this is another way of specifying the truth table. This is a very different way of specifying the truth table. It's not the truth table that we're used to so far, as you can see, because it doesn't really have the inputs A and B over here, right? Even though A and B are inputs. But this is a very compact way of specifying the truth table of a mux. Basically, if the select signal is 0, C evaluates to A. If the select signal is 1, C evaluates to B. Simple truth table. Of course, if you really want to actually build it, then you actually need to maximize this truth table to such that it includes the inputs. Okay, this is not a conventional form, but you can use this for a mux. Okay, your task, actually I'm going to do this task in the next slide. You can draw the schematic for a 4-input mux, 4-to-1 mux. You can do this in two ways. You can do this as gate level, as a combination of basic and or not gates, clearly. Or you can use this as a module level, as a combination of 2-input 2-to-1 muxes. Basically, if you already have this, you can combine the muxes. So this is a 2-to-1 mux. What if you had 4 inputs, A, B, C, D? Well, if this is your building block, you can replicate it, put CD, and have another select line, right? And then you have another mux over here that selects between the outputs of those two muxes. Right? That's a 4-to-1 mux built from 2-to-1 muxes, which is really this one over here. Basically, this is a 4-to-1 mux. This is a 2-to-1 mux. Select 0 goes to this one as well as this one. Basically, this is 1-bit select signal. It selects between D0 or D1, and D2 and D3. And this is the second bit. If your select signals are both 0, 0, for example, you will get D0 at the output. If they're 0, 1, you'll get D3 at the output. If they're 1, 0, you'll get D1 at the output. If they're 1, 1, you'll get, wait, I messed up. If they're 1, 1, what do you get at the output? You'll get D3. If there's 0, 1, okay, let's start from the beginning. It's not magic, as you know. If there's 0, 0, what happens here is you get D0 over here, you get D2 over here, but you get D0 over here. Okay, that's easy. If there's 0, 1, you get D0 over here and D2 over here, but you get D2 over here. I said D3, that was wrong. So you get D3 over here, D2 over here. If they're 1, 0, you get D1 over here, D2 over here, but this is 0, so you get D1. If they're 1, 1, now you get D1 over here, D3 over here, but you select this one, which is D3. Okay, I know how logic works, that's good. So I can simulate the circuit clearly, right? So that's basically the idea. So this is a hierarchical thing. So if you want to build an 8-to-1 mux, now you replicate this over here, add another select input, right? That's the idea. But of course, you don't need to do this. You can actually do this. This is the gate level realization of this 4-to-1 mux. We use directly these gates. You basically have two select inputs, and depending on what the select inputs are, you select D0, D1, D2, D3. Basically, to select D0, your select inputs need to be both zeros, right? If they're both zeros, you basically get D0. And you can do the same thing, basically. This maps to this in the end. But you can see that this is also a min terms over here. It's interesting, right? And this is actually very similar to a programmable logic array that we will see later on. You have an AND block. You basically form the min terms over here, and you basically do the AND of the min terms that lead to a 1, and you OR these things at the end. So AND and OR blocks. Sum of products is essentially that, right? Sum of products is really AND OR blocks. Okay, so we will see the sum of products. You can map everything to a sum of products form, because that's the canonical form of a Boolean logic, and in the end, a circuit implements a Boolean logic. Okay, so let's talk about full adder. Any questions on the multiplexer, decoder? These are basic logic structures that you will use in the future, I guarantee that. Okay, full adder. How many people know about the full adder? Okay, how many people know about binary addition? Basically, we're going to do binary addition. There are multiple different forms of binary addition. This is one form. But basically, it's similar to decimal addition. You go from right to left. You do one column at a time. And you basically, each bit addition generates a sum and a carry bit. Very similar to decimal, right? Except you're operating in the binary number space over here. So basically, you get a sum, and you also get a carry, and the carry gets input to the next bit. So you really add A1, B1, C1. You get a sum 1, and you get a carry 2, which you add to the next one. So by nature, this is really serial, right? It's a bit, you basically serialize the carry generation. And if you want to add a 32-bit number, the carry that you generate from bit 0 needs to go to bit 1, needs to go to bit 2, bit 3, bit 4, bit 5, and then eventually bit 31. And that's really the hard part in addition, because it's a serial process. Okay, Basically, you can do the truth table of this binary addition on one column of bits within two n-bit operands. So in this case, I have 1-bit operand over here. So basically, each column, each bit is added that way, this way, AUI, BI, and carry I. And the outputs are, it has 3 inputs, it has 2 outputs, carry I plus 1. What should the carry over be? And the sum. And clearly you can implement this using sum of products form, which we will do later on, basically. So binary addition really is n 1-bit additions. So you do this 1-bit addition, you generate the carry, you generate the sum is the output, carry goes to the next circuit that implements exactly the same thing. And then it generates another carry, another sum is fine, that's the output. The carry goes to the next circuit that implements the same thing, right? So it's really a serial process, as we will see. So the sum of products of the 1-bit addition is this. Basically, this is our 2-level representation, right? This is the AND logic, and this is the OR logic. And what is sum of products? Okay, I'm going to go through this again very quickly. Carry out, that's one output. It's 1 in 4 places. A bar, B, carry. A, B bar carry. A, B carry bar, and A, B carry, right? Basically, all of those cases need to be ORed, and that's when the function evaluates to 1. If any of those cases is true, if any of those min terms are activated, then you get a 1 at the end. You do the same thing for sum, as you can see. There are 1, 2, 3, 4 cases again, where the sum is 1. And you can see that there are 4 inputs over here. And you can be sure that those 4 inputs are connected to the min terms that are corresponding to these 1s over here, which is 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. So you can be sure of this. Basically, what we've done is we've converted the sum of products and we built a circuit that directly implements the sum of products form. Makes sense, right? So this is a very easy way of generating a circuit. Of course, it's not the minimal way. Okay, we'll see the minimal way later. So that's the underlying implementation. Now you can say that this is a module. This is my module for full adder. It does 1-bit addition. Now I can use it to do 4-bit addition. Basically, how do you do a 4-bit addition? You basically connect these 4 1-bit adders this way. This is the 0th bit. Initially, carry in is 0. Clearly, there's no carry in because there's no bit to the right of you. And it produces a carry out that goes into the 2nd bit, which is bit 1, and produces a carry out that goes into the next bit, and produces a carry out that goes into the next bit, and this carry out is discarded in the end. But this is your sum, basically. This is one way of building a 4-bit adder from a single bit adder, from 4 1-bit adders. Makes sense, right? There's no magic in this. And this is essentially how some adders work. It's called a ripple carry adder. Okay, so this is basically implementing what I've shown over here. You can convince yourself of that, and you can actually go and put these inputs to your truth tables of all of these full adders, and you can convince yourself that you will get the right result in the end. I'm not going to do that. This is simulation. But this is exactly how some tools work also. Once you build these tools, you can actually simulate things, and you can actually verify that the output is what you actually intend the output to be. And if the output is not what you intend the output to be, you can now go and debug it and figure out where the problem is, right? So all of the things that I'm describing over here in the slides are actually used in some computer-aided design tools to verify your circuits, assuming that you give the test inputs and the correct outputs to them. Okay, so this is a 4-bit adder. If you want to add 32-bit, two 32-bit numbers, this is how you do it. This is from your book, Harris and Harris. You can see that each of these is a single full-bit adder, and you have 32 of them. Makes sense, right? You're basically adding two 32-bit numbers. And your building block is a single adder that can add two 1-bit numbers. Now you can, of course, extend it. If you're adding two 1024-bit numbers, you have a huge adder, right? 1024 adders. Make sense? Clear this is expensive. Clear there are implications on time. How long does it take, right? Because now you do the addition and then carry comes, and then you do this addition after this carry is available. So basically the critical path, we will see, we'll have a lecture on timing. We're not talking about timing right now. How long does it take for this circuit to evaluate? We didn't talk about that as much, right? But in the end, we will talk about critical path, meaning when does the output stabilize for the circuit. And the critical path of the circuit is really this carry generation. It goes from this path, and the carry out or sum, either of those are the last, but this is really on the critical path, carry 30 over here. So it takes a long time to generate this carry. So as a result, people have actually designed many different adders. And this is from your book. I'm not going to talk about this in detail, but people said, okay, this carry takes a long time to propagate over here. Can I not build this adder exactly this way? Looking at every single bit to generate the carry is just too long. Why don't I combine 4 bits together? I basically use a specialized circuit to do the 4-bit addition. I don't do a 1-bit addition. I specify a truth table, 4-bit addition, 2 numbers, A, B, each of them 4 bits. So the inputs are actually 8 bits, plus a carry. You can see that. The inputs are 8 bits plus a carry, and the sum. Now you generate the sum of products form. You basically design a circuit for that block. And this is your circuit. One way of designing the circuit. And this is the carry generation circuit. It's very different from what we've seen earlier. Basically, it's a specialized circuit that is optimized to generate the carry as soon as possible. And that carry becomes available much earlier than the carry out of the 4th addition becomes available much earlier than it would become available if you're doing this rippling over here every single bit. Because you really customize your circuit so that you generate this carry as soon as possible. That's the idea. And you can see this block. You can read this actually, this is beautiful. There's actually a lot of work on adder design in terms of how to actually generate this carry as soon as possible. This is called carry look ahead. Why is it look ahead? Because you're really generating the 4th carry as soon as possible so that this block can start operating with that 4th carry, so that the next block can start operating with the 8th carry. And then the next block can start operating early with the 12th carry, ... as opposed to generating the carry slowly. And this is faster. This is faster, but it turns out this is more overhead, and there are trade-offs related to this. This is, circuit-wise, this is more overhead. Okay. Does that sound cool? Okay, so you can play tricks. So you can also ask the question, okay, why do I do this? Why don't I treat the 32-bit addition as a truth table that has a 32-bit A input and a 32-bit B input and a carry in, where the carry in is 0 because there's no carry in. And then you minimize that truth table. You could do that. That's a specialized circuit for a 32-bit adder. You cannot do 1-bit addition with that. Well, I guess you can, but it's wasteful, right? So that's the beauty of designing logic, right? If you want to design a 32-bit adder, you can do the truth table, you can minimize the circuit, and you can have a specialized 32-bit adder. Or you can have a 1-bit adder and basically put them together to get a 32-bit adder. And these are 2 different ways of designing the adder, and they have different trade-offs in terms of circuit size, in terms of delay, in terms of power consumption. Later, when we see sequential logic, you will see that there's another way of designing this adder. This is kind of stupid, right? Meaning you have, for every bit, you're doing the same thing. And you have 32 things. People realize very quickly that, okay, this is combinational. I'm not storing anything. But if I had the capability of store what I calculated previously, I can get away with a single bit adder, just one of these. What do? A0, B0, I feed them in the first cycle. I get the sum. I get a carry out. I store the sum somewhere in some place that I don't forget. Now what I do is in the next cycle, we're going to see the notion of cycle later on. I take this carry 0, plug it here, and put A1, B1 in, the same circuit. In the next cycle, I'm going to calculate the next bit. And I store the output. And the next cycle, the inputs will change again. Carry 1 will go here. A2, B2 will come. I'm going to compute the next bit. I'm going to compute the next bit. So I can get away with a single adder to do a 32-bit addition, except I do it 32 times in the same adder. So that's another way of doing the addition. But of course, that's not combinational now. Remember, combinational is you don't have any memory. You don't store anything. We're talking about combinational circuits. So that's the beauty of going sequential. If you start remembering things, you can actually minimize the circuit even more, because then you realize that I don't need 32 adders over here. I just need a single 1-bit adder, and I use it over time, many, many times, to do a 32-bit addition. In fact, I can do a 1,000,000-bit addition of two numbers that are 1,000,000 bits by using a single-bit adder, very simple circuit, 1,000,000 times, right? So you don't need expensive circuitry to do a 1,000,000-bit addition. You just use the same circuitry over time. That's the idea. And that's the power of sequential logic, as we will see tomorrow. Okay, but this is not sequential, this is combinational. Okay, so recall the, basically, now that we're going to talk about PLA, we're done with the adders. Any question on adders? This is a fascinating topic. People try to optimize the speed of adders, and these are not the state-of-the-art adders. And power consumption is some other thing that we're not going to discuss over here. If you really are interested in adders, you should really take a computer arithmetic course. Okay, but basically, so the next and final building block that I'm going to talk about is the PLA. PLA is programmable logic array. Actually, you've seen many examples of this. Essentially, sum of products form leads to two-level logic. And this two-level logic can be nicely realized with something called a programmable logic array. And I will show you more, I don't want to call it formal, but more formalized definition of programmable logic array. But this is actually like a programmable logic array. Basically, you have the capability to generate any minterm, and basically, and any minterm. Basically, you have the capability to generate any minterm, and you have the capability to OR them in any way you want. That's the idea. For example, this function has 3 minterms. So you can generate 3 of these minterms, and you can OR them. Of course, this is showing a part of the PLA. So in a real PLA, for a 3-input function, you should really have the capability to generate 8 possible minterms, right? And then this OR gate should connect the ones that you want. Okay, basically this is it. This is what I just said. You have these 8 minterms that you generate. This is a programmable logic array, so you have a 3-input function. And you can basically, these are potential outputs. So here I have one output, y. But you can have 3 outputs, let's say. There's a PLA that can take 3 inputs and that can generate 3 outputs. Basically, the outputs should be a combination of any possible minterm of these 3 inputs, which is really the canonical sum of products form. And you have some connections that you need to fix, of course, so that you can connect any minterm to any of the outputs over here. Okay, basically this logic is a structure. It's a very common building block for implementing any collection of logic functions one wishes to. That's why it's configurable. So you can implement anything on this as long as you have that, you have enough, you don't exceed the number of inputs, and you don't exceed the number of outputs, of course. So basically, it's an array of AND gates, as you can see, followed by an array of OR gates. That's why it's called a programmable logic array. Programmable because you can program the connections that I don't show you over here. These are generated. These are the minterms over here, and then you can connect the minterms to the outputs. So how do you determine the number of AND gates? Basically, remember the SOP. The number of possible minterms is 2 to the n, where n is the number of inputs, right? Basically, for an n-input logic function, you need a PLA with 2 to the n n-input AND gates. That's the idea, and you can see that over here. You know that well. How do you determine the number of OR gates? Basically, this is really a function of your PLA. So somebody creates a PLA, and it gives you, okay, you can only have 20 outputs. In this case, it's 3 outputs. It depends on the function in the end that you're going to implement. Your function may have only 1 output, right? Then you don't use these 2 outputs. Your function may have 10 outputs. Too bad. You cannot implement on this PLA. You need to have multiple PLAs. Okay, or some different PLA. Basically, this is the number of output columns in the truth table. So let's take a look at this PLA example. How do you implement a logic function in this? Basically, you need to connect the output of an AND gate to the input of an OR gate if the corresponding minterms include in the sum of products form for that particular output. That's the idea. We've already done this, actually. So it's a simple programmable logic. So basically, programming a PLA means you program these connections from the AND gates to AND gate outputs to OR gate inputs to implement the desired function as specified by the sum of products form. So you've already seen some programmable logic, which is FPGAs. You don't know exactly how they're implemented, but you have a high-level idea. But this is one example of programmable logic. You can build an FPGA this way, actually. You need some memory, but we haven't talked about memory yet. This is combinational again, right? Okay, an FPGA actually uses more advanced structures, as we saw in lecture 3. If you want to know more, Harris and Harris' book actually talks about FPGAs after it talks about programmable logic arrays. I'm not going to cover that, but if you're interested in how an FPGA does it, Harris and Harris has a very good basic treatment of it. Today's FPGAs are, of course, much more complicated, but the basic ideas that are there in Harris and Harris are in FPGA. Okay, basically, this is the PLA example, and I actually borrowed this from Harris and Harris. Inputs, M inputs, you have an AND array. These give you the implicants, or minterms, and then you feed them into an OR array, and then you get the outputs. So this is one example function that you implement with a PLA. Basically, these are the connections, and this is one form of specifying it. Basically, this is the AND array. This leads to A bar, B bar, C, for example. This leads to A, B bar, C, and this A, B bar. And then you connect them. Basically, X is equal to OR of A bar, B bar, C, and A, B, C bar. And Y is equal to A, B bar in this case. So another way of looking at it is this. So this is a simplified way. Actually, I should have shown the previous one before, but these two are equivalent. Basically, a dot means you're connecting that thing to here, which means also this. Basically, this is exactly the same thing. A bar, B bar, C, A, B, C bar, A, B bar, and this is your output, and this is Y. So some of the things are not shown over here, but you can take a look at the book. So let's implement this full adder using a PLA now. So this is our PLA, and we're going to map our full adder. And essentially, a computer-aided design tool will do what we're going to do right now. They can do this. And we're going to start with a truth table of a full adder. You know this truth table. And this is the PLA implementation. I guess that was so easy, right? But what did we do to get here? Basically, PLA is sum of products form. And you already know how to form the sum of products form, right? You basically take the minterms that lead to a 1 in the carry and connect them to the OR gate whose result is the carry out. And we know that there are 4 of them, 1, 2, 3, 4. And we connect the minterms that correspond to those 4. We can verify that again. And then some do the same thing. And this PLA happens to have 1 extra output. We don't connect it to anything because an adder doesn't need a full adder. A single bit full adder doesn't need a third output, right? That's the idea. So based on everything we learned in this lecture, a computer-aided design tool can go from this truth table of the adder and program this PLA itself automatically. You just need to specify the function you want to implement. Makes sense, right? And of course, this is PLA, this is not minimal, right? Because you can implement any 3-input function, any 3-input, 3-output function with this, right? That's why you have a lot of hardware that's not used over here. And you can see that this is not a minimal form, but it's a programmable form. It enables you to implement any 3-input, 3-output function completely automatically. Okay, basically, this input should not be connected to any outputs because it doesn't activate any of the outputs, as you can see. So that's why it's not connected. And you can see that we do not need this output. And you can clearly see that this is not minimal. Okay, so this brings me to something called logical completeness. Have you heard about logical completeness or Boolean completeness? Okay, good. You're going to learn at least something in this lecture. And this is very important. Basically, any logic function we wish to implement can be implemented with a PLA. Why? Well, PLA consists of only AND gates and OR gates and inverters. We just need to program connections based on the sum of products of the intended logic function. Basically, the reason why we can do this is the set of gates, AND or not, is logically complete. Because we can build a circuit to carry out the specification of any truth table we wish, without using any other kind of gate. That's the idea. So AND or not are logically complete. In fact, NAND is also logically complete. Because you can convert any operation to an AND. And you can convince yourself by looking at the laws we've covered. NOR is also logically complete. You can convert anything into NORs. Because OR and NOT alone are logically complete as well. And OR alone are logically complete as well. Basically, PLA is actually nice because it gives you AND or NOT at the same time, but you don't need all of this also. You could actually have, with some more effort, a circuit that includes only NAND gates. In fact, that could be one of the homeworks that you will do. You convert an adder into only NAND gates. You can design this full adder using only NAND gates or only NOR gates. And actually, you can design anything using only NAND gates. And that's the notion of logical completeness. You can prove this. I'm not going to do that for you, but it's relatively easy to prove once you actually look at the Boolean algebra. You can also prove that AND gate by itself is not logically complete, because you need inversion. And if you don't have an inverter, you're not going to be able to express some of the min terms. If you have an inverter and a NOT, and an or an AND, then you can actually express any logical gate. OR by itself is also not logically complete. You do need the inversion. NAND itself is logically complete because it does inversion as well as AND at the same time. Right? Okay, so if you want to have more of this, I would suggest reading this part, basically chapter 2 in full. I'm going to talk about tri-state buffer actually right now, because I think it's going to be important, and we're going to have a little bit more fun. Chapter 5, actually, I've been covering some things from chapter 5 also, and it'll become important later on. Chapter 5 actually has some more material that we're not going to cover. Like it talks about arithmetic and stuff. We're not going to cover that in this course, but if you're interested, you can look at arithmetic in that chapter. The arithmetic that we're going to cover is limited to the adders, like this. Yeah, basically, this is what I would recommend. Any questions? Okay, now you know programmable logic also. That's the beauty of combinational logic. You can do anything you want with programmable logic. Let me introduce something that you have not seen before, hopefully. How many of you have seen a tri-state buffer? Okay, some people have. How did you see it? Your free time, okay, great. Well, yeah, that's right. Not everything you learn has to be at school, which is the right mentality, actually. But basically, a tri-state buffer is very useful because it enables gating of different signals onto a wire. Meaning, using this buffer, you decide whether the signal that you have should be put on the wire or not. That's the idea. It looks like this. It looks like a buffer, but it's not a buffer. It is a buffer with an enable signal. So it has two inputs, the data input and the control input. Data input is the input that you are or are not going to pass to the output, and control input is the enable input that enables or disables the buffer. Now, if the buffer is enabled, the output gets the value of the data input, which is this part of the truth table. If the buffer is enabled, output is essentially a buffer, right? If the buffer is disabled, the output doesn't get connected to the input, meaning the output value is floating. So now I've introduced something called a Z value. That's a floating value. That doesn't mean that it's an incorrect value. That just means that this wire is not being driven by this input. Makes sense, right? The output is not driven by this input. The transistor is not connected, meaning that somebody else can drive this, assuming they're connected to it. That's the idea over here, right? This is very useful, as we will see in multiple constructs, and we will see these tri-state buffers later on. And I will actually show you an implementation of a MUX using tri-state buffers in a little bit. So these could be used to build logic circuits also. It's still Boolean logic, but there is some attached to it. There's an unspecified value called floating value. Okay, this is called a floating signal that is not driven by any circuit over here. So open circuit or floating wire are different names for it. So basically, what is the use of this? Imagine a wire connecting the CPU and memory. At any time, only the CPU or memory can be driving that wire. It's a bus, let's say, but not both. Tri-state buffer is a perfect perfect thing to put to load those wires. Basically, you can have two tri-state buffers, one driven by the CPU, the other by memory, and ensure at most one is enabled at any time. That's an example. So you have CPU, you have memory, they have a shared bus, and sometimes CPU is going to send something to the shared bus. I'm not showing where the bus is connected, but this is the part that really matters in the end. If the CPU wants to put something on the bus to communicate with whatever, you set gate CPU enable this tri-state buffer, and disable this tri-state buffer such that CPU can put whatever it wants. And if the memory wants to put something on the tri-state buffer, you disable this one and enable this one such that the memory can put whatever it wants. Of course, you need to have some control logic to set the enable bits of these tri-state buffers. And that's what we're going to learn later on when we build a microprocessor. When you're building a microprocessor, you need to control these nicely. Because if you set both of them to 1, you're in trouble, right? Because memory is generating an output, CPU is generating an output. If both of them are 1, then basically what happens is you actually electrically loaded the tri-state buffer too much. Okay, next time we're going to pick up from here, but this is another example that you can study on your own. I guess we'll start tomorrow. Yeah.